All right, thank you, Chava. So it's my great pleasure to introduce Mengdi Wang. Like I said, I did not have the pleasure to meet her in person so far, so this is also my own introduction to her. I've been following her work for a couple of years now. She's been doing very, very impressive work in reinforcement learning theory, in stochastic optimization theory, in system identification, a number of topics like that. She finished her PhD in 2013 at MIT under the supervision of Dimitri Bertsekas, and moved on to be an assistant professor to Princeton, where she's now an associate professor. And she's currently on leave at the DeepMind Foundation's team. And she has a number of awards for her fantastic work. I'm going to list a few of those, like the Young Researcher Prize in Continuous Optimization from the Mathematical Optimization Society, the Google Faculty Award, NSF Career Award, MIT Tech Review, 35 under 35, a really impressive list of achievements. But I think that her work really speaks for itself. I learned a lot from her papers, so it's very well fun to follow her in Google Scholar and keep following her amazing papers. And I'm really curious to hear what she has to say today. Please welcome Mengdi.
Okay, can you hear me? Yes, okay. Thank you, Gregory, for the very nice introduction. Okay, so it's my pleasure to share our recent research here with the group. And so I'm going to turn off my camera and focus on the slides. Okay, so this works, right? Okay, you guys are nodding. Okay, so I'm going to talk about off-policy evaluation today, and also recently I got really into analysis of regression, which is like a simple subject in statistical learning, or we thought it was simple, but increasingly I think I started to feel like RL has a close and deep connection with regression, and hopefully I can share some of my ideas with you through this talk by focusing on the off-policy evaluation problem. So this is joint work with Yaqi Duan, so a PhD student at Princeton University, and I stole a few pages of slides from her presentation. Okay, yeah, and I'm currently affiliated with both Princeton University and DeepMind Foundation team. Okay. Okay, so what's the problem definition? So the full name is off-policy policy evaluation. And usually people call it off-policy evaluation just to keep it short. Okay, so the problem is very clear. So we know that we have a Markov decision process. To keep it even simpler, let's say that we have a fixed horizon H, but this could be easily generalized to infinite dimensional discounted problems. Okay. And now we have some data. So our data take the form of a collection of transition tuples. So in each sample, we have a tuple of state, the action implemented, observation of a next state, and observation of a reward. Okay, so that's the data we're going to work with. And so we know that the data is generated by some policy. We call it the behavior policy. But generally speaking, we don't really know what the behavior policy is. And of course, we don't know the model of the MDP. We don't know the transition function, the little p. And we don't know the reward function, little r. We just have a collection of episodic trajectories generated by some policy. Okay, and the problem we want to study is, oops, it's not a good idea. The problem I want to study is actually a very simple prediction problem. We want to be able to predict the value of a new policy. Let's say that we have a new target policy, and we want to predict what will happen if we implement a new policy. And where we know what the target policy is, and also let's say that we fixed an initial state distribution cosine 0 right here. Oops. So now we only want to estimate a single value, the value of a new target policy from a fixed initial distribution. Okay, so this is clear. Okay, so why do we care about this problem? This seems to be a problem much simpler than RL in general, right? Usually we want to optimize and we want to learn online. Okay. How do I move to the next page? What happens? Okay. So we care about this basic problem because in many applications, we actually cannot run experiments very easily. So this particularly occurs in medical applications and in science applications. Usually, we might have some public data set or experimental data set that we have collected already. But based on the data set, we cannot run cheap experiments. We really want to do our best with the existing batch data. And the existing batch data could be pretty small. And then we care about what can we do with existing batch data. Okay. So OPE, off-policy evaluation. So I think of it as actually a first-order critical task. Or I think it's even a prerequisite for RL. So first, in data-limited applications, we have to work with batch data. Say that I have some clinical data, and we want to predict what happens if we apply a new treatment policy. Right? We don't even have to talk about optimization yet. Maybe the doctor come up with, hey, I think we should do this. We should try this. This might make sense. But we want to be able to predict what would happen if we implement a new policy, right? And this also happens a lot in trading. Like one has to predict what will happen if we implement a new trading policy before actually trading it, because one could lose money, right? And so off-policy evaluation is actually also important in online RL. Because think about online RL, our agent is collecting new data constantly. And every time it collects one single new data point, it actually has a new off-policy evaluation problem. It has to make best use of the experiences collected so far. And then that data is going to be used to improve the policy and to do exploration. Right. So we really care about, statistically speaking, when can we make off-policy evaluation work and when it doesn't work. Okay. Okay. So the primary question we want to answer is, how do we optimally predict the performance of a new policy from batch data? And we care about statistical optimality and the minimax optimality. Okay. So first, I want to make an assumption. So in order to be able to generalize well from batch data, we need function approximation. I don't want to work with the tabular case. That case is just too hard. So let's say that we're going to work with function approximation. So I'm listing one assumption. Actually, there could be other alternative assumptions. So I'm making one assumption about approximating value functions and actually state action value functions. So suppose that we want to actually approximate the Q function of the new target policy. So we have a function class Q. And let's make an assumption, which is actually a bit strong. Let's make an assumption that this Q function class is sufficiently expressive, meaning that if I apply the transition operator of the true underlying process to a function f in the Q function class, then after application, I get another function which is still in the same function class. So this will guarantee that we can approximate Q functions iteratively without losing anything. And to make it more general, one can impose additional misspecification error and do misspecification analysis. But I'm not going to do it in this talk. Let's simply assume that this is already what we have. We already have a good Q function class, so that the unknown transition operator is closed within that class. I mean, the class is closed under the transition operator. Okay. Wait, I think I should use my mouse. Okay. So let's get back to the tabular case, the tabular MDP, just to understand the problem a little bit. So in order to evaluate a new policy from batch data, the most intuitive method is by importance sampling. So for example, if I want to estimate the one-step reward function of a new policy, but our data, this little r, each little sample reward is generated by another policy, then naturally we want to reweight our samples by the ratio between the probability for choosing the action under the different two policies, right? So this is something that will naturally come to our mind. And now if we care about evaluating the value, which is a collection, the sum of rewards over a trajectory, then usually one might expect to actually estimate this density ratio, which is the ratio between the occupancy measure under the target policy and the ratio of the occupancy measure under the behavior policy. Okay, so we know this very well from simulation, right? This is something that comes naturally. But if we think about this, we actually have a lot of challenges to address. So for example, if we don't have any function approximation, we're dealing with the tabular case. And we certainly know that whenever we have some ratio between probabilities, then this ratio could be pretty large. And that could make our estimator to be pretty bad. And also, if we want to estimate this density ratio between two occupancy measures, this is an even harder problem because then we have to do density estimation. And we usually don't do density estimation in RL, right? And another challenge is we don't know this pi bar, this behavior policy. Because, for example, think about like we have clinical records which were generated by some doctor. The doctor himself cannot really tell us in closed form what is the policy he's implementing, right? Because the doctor is using his own judgment. But we know that there's some underlying policy, but one might have to estimate that policy. So if we want to estimate a policy, or we want to estimate a density ratio, and then we use that in the denominator, then we can imagine that this could actually be pretty noisy. Okay, so what happens is basically if we try to use importance sampling together with tabular MDP, then we actually run into serious trouble because usually we want to invert a probability which is unknown, which could be small, and we have to estimate that. Okay, and also there's a problem which is sometimes referred to as the curse of horizon. So the curse of horizon means that when we try to estimate this density ratio, this term, this density ratio is the ratio between densities over the sample path. But our estimation error could grow exponentially as the horizon becomes large. Okay, so there are a lot of methods and efforts trying to improve importance sampling approaches. So importance sampling approaches are actually very advanced today. So I'm not giving the details, I'll just illustrate the idea. So basically, there are many variants of importance sampling approaches. And basically, one try to estimate, I think this is a typo, this should be V. One try to estimate the weight, which is a density ratio, using function approximation or some function fitting. And then after we estimate this weight, it's a bad idea. After we estimate this weight W hat using one way or another, then we try to use this weight to do importance sampling and estimate the value V hat. So one method, which is known to be minimax-optimal in the tabular case, is known as marginalized importance sampling. And the idea is super simple. So basically, we estimate the weight from stage 0 to stage 1 to stage 2, basically in a forward manner. In other words, it's in some sense, we are estimating the occupancy measure of the new policy in a forward manner. And finally, we have all the occupancy measures and all the weights. And then we can do important sampling approaches. And this can be done together with function approximation I think, in a few recent works this year. Okay, so this is one class of approaches trying to approximate this weight function and then do forward learning. So I want to talk about regression. So I skipped a lot of details about important sampling, and because I want to talk about value function-based methods. Okay. So what if we do this backward in a way that's actually closer to optimization methods for MDP? So instead of estimating weights for important sampling, let's approximate Q functions directly by regression. And this is actually a very old method. It's well known as fitted Q iteration for solving MDP based on samples with function approximation. And we can use fitted Q iteration for evaluating a fixed policy by simply omitting the optimization step. Okay? So we do this. So we start with the last Q function. We assign it to be an O0 function. Okay? And then we just iterate the Bellman operator, but with a linear regression step. So here, f is the function Q that we're trying to fit. And we're fitting f such that it should be close to the expectation of the future Q functions plus reward. And if we look at this fitting step, this is really linear regression with the latest Q function as the target. Okay? And finally, after we get Q0, the initial Q function, then we can simply use that, taking integral to evaluate the policy value. So we call it V hat FQI, policy evaluator using fitted Q iteration. So we can see like in this approach, we're doing things backwardly. So we started with the last Q function, and then we do model regression backward, and finally we get the initial Q function and the initial value. Okay. So comparing the two approaches, important sampling and the Q function and fitted Q function iteration. So we can see that they seem to be entirely opposite in terms of how it works. In important sampling method, we approximate the weight by iterating Bellman operator forwardly. And in fitted Q iteration, we iterate Bellman operator backwardly. Okay? So later we can see that they're actually primal dual to each other. Okay, so lastly, I want to talk about another approach, just plug-in estimation. So plug-in estimation would be like the simplest approach in statistics. Say that we just estimate the model, and then we use the estimated model to just plug it in. Okay, so with a Q function class, what we are going to do is I'm going to approximate the transition operator under a target policy pi, this p hat pi here, and we fit it directly to data. And we are using this known target policy in data. Okay, and then so basically so this is one data point, and this is what happens next. Okay, does that make sense? So I'm simply fitting the transition function from the data. And we can also fit the instant reward function similarly by regression. Okay, so know that we can always do this for any general Q function class. It doesn't have to be linear. So once we estimated the model and we estimated this little r, so we have a model estimate, which could be pretty inexact. And then we just plug p hat and r hat into the Bellman equation, and we solve it. And this is just a finite horizon case, but we can plug it in to any Bellman equation, right? And then we simply estimate the plugin policy evaluator from the solution to the empirical Bellman equation. Okay, so now we have three approaches. One forward approach by importance sampling, one backward approach by regression and Q iteration, and another is plugin. Okay.
Sorry, Mengdi, I have a question about this plugin estimator. So here you're optimizing over these functions G, but I guess for this to make sense, then this G function should be like an indicator or something. If I'm thinking about like the tabular case, right? If I want to get like an accurate estimator of my true transition function, then G should include like all the indicator functions. I'm just trying to understand what are
G should include all the indicator functions. Yeah, exactly. So G is really just a mean operator.
Right.
Yeah, it could be a smaller dimensional function, but you're right. In tabular case, this P hat is really just an empirical transition matrix.
Right, and I guess maybe you're going to say a few words about what assumptions you need to make about Q for this to be compatible with the rest.
Okay, yes.
I'm curious about that, but I guess we're going to get to that.
Okay. Yeah.
Sorry for interruption.
And a bit more words on just plugin estimator. So if our Q function class is a finite dimensional linear function class, then the estimated P hat takes this empirical form, corresponds to an empirical transition kernel. And this empirical transition kernel, I believe, is something we are very familiar with. It's actually related to the conditional mean embedding for linear regression. Okay, so so one might ask, okay, so why do we care about plugin estimator? No one's going to do it. So I actually want to mention that I think plugin estimator is actually a fundamental approach, because plugin estimator means that we can simply fit our model to some function class, and then we use the fitted model to estimate the value of a new policy. So we're actually decoupling this estimations step and the policy evaluation step. So after fitting the model, we can compute the estimator using any algorithm that works for our policy evaluation. And also, whenever we fit a state-to-state prediction model onto a batch data set, and then we get a simulator, right? That's usually what we do. Given some data, we build a simulator, and then we use the simulator to learn the optimal policy to predict new values. So whenever we do this, we're essentially doing plugin estimation, but just plugin estimation with a particular model which we use to build a simulator. So in some sense, plugin estimator is a more general view of what's happening when we learn from batch data. Okay, so how do they all related? So basically, if the function class Q is linear, and let's ignore this rich penalty term for simplicity, then those three approaches we just mentioned are equivalent, meaning that the three estimators as a function from the data to the rails are equivalent functions. Okay. I think similar observation about FQI was also made by Nanjiang in actually a paper last year or 2 years ago. And we can actually show that this equivalence holds more generally for a broader range of methods, which I don't have time to delve into. Okay. So basically, I think a very strong but short message is we are talking about all the seemingly different algorithms, regression versus importance sampling. They seem to be entirely different, but they're actually computing the same estimate. So basically, convergence of the algorithm isn't the key, because we can always compute the plugin estimator using one way or another, but it is the estimator itself that is what we care about. Okay?
Right, so just a quick question here. So you say that the condition is that Q is a linear space, but I guess you still assume that Q is closed under the transition operator of
yes,
the
that was the assumption.
Right.
But okay, I would say this is a little okay. I cannot formally say that because, for example, this importance sampling estimator they require different assumptions on Q. But if we use the same Q for those two estimators, although they require different assumptions, but what they compute are equivalent.
Right.
So there's a notion, actually, one can make assumption in the Q space, or one can make assumption in the space of importance weights. But that they're actually the same Q, and they correspond to the identical estimators. So this theorem says that if Q is a linear space, then the two estimators are equivalent. So this actually is not making assumption about what's going on with the model and the Q, because the estimators are just functions, right? Are functions of Q.
So you don't need to assume that the MDP is linear or the transition model is factored.
Yeah, to get upper error bounds, we need that assumption. But the equivalence of the estimators holds actually generally, because the estimators are just functions from data to a real number.
Right. Perfect.
Okay.
Yes. Very good. Thank you.
Okay. Good question. So next, let's prove some theory. So since we just showed that all these different estimators are the same, so let's simply call them plug-in estimator to include all. So we show that the plug-in policy evaluator actually has near optimal error. So this is an upper bound. We'll complement this with lower bound later. Okay, so we had this leading order term, which we need to explain. And we have a small order term, which is actually on the order of 1 over big N, N being the sample size. Okay, so this error bound holds as long as the sample size, N, is bigger than poly H times D. D is the dimension of the feature space. Okay, so this is quite important because if we think about the tabular case, or what happens with importance sampling, usually if we didn't get one particular state right, the full algorithm could just blow off. But to get every state right, then the sample size has to be linear with respect to S. But when we do function approximation, and at least in this simple linear space, N has to only be as large as dimension. Okay, and we have this Q-restricted chi-square term. I'll explain a bit later. So let's just say that this chi-square term measures the hardness of the policy evaluation problem. It measures the distribution mismatch between the two policies in a feature space. So I also want to emphasize that in this theorem, we do not require a typical coefficient concentration condition. I mean, for those who worked in this area, you might have seen this condition, which requires that the entry-wise density ratio between the two occurrence measures is uniformly bounded. So this condition basically says that two policies have to be pretty similar. And usually to get a good error bound, one needs this condition. But we actually don't need this condition because we actually allow the two policies to be quite different. But we only require that their mismatch in the feature space is small. Okay? So we have an upper bound. So let's, oops, my apology, I have a typo. This part, let's ignore this highlighted part. Yeah, I should, okay. So this is the definition of the chi-square divergence. So as you can see, this is, okay. Let's ignore this part, okay? So it's a typo. So this is a definition of the chi-square divergence between two policies over a restricted function class. And as you can see, this is a variational form of divergence, and the Q function class shows up here. Okay, so this is actually a dual form, and it has a primal form, which can be viewed as the projection of the density ratio onto a lower dimensional space. Okay, so what's important is this chi-square measures the distributional mismatch that is only relevant to the function class that we care about. To give you some examples, so in the tabular case, so Q, this function class Q is just the entire space. And then this mismatch reduces to the typical Pearson chi-square divergence. And that divergence could be pretty large. for two discrete distributions. Okay. But if we use a finite dimensional linear model, then this divergence could actually be bounded by comparing the two covariance matrices from the two policies. So it becomes a relative condition number. As you can see, now the covariance matrix is really summarizing variation and distribution in d-dimensional space. So this is a much smaller mismatch in a lower dimensional space. So for the same two distributions, measuring their divergence in the tabular case would give us a much larger error than measuring their divergence in the feature space. Okay, so basically, if we have a well-behaved function class, although the two policies might seem to be very different, but their restricted chi-square divergence could be small if we have good function class for generalization. Okay, so that's the upper bound. So we also established a nearly matching minimax lower bound. So the minimax lower bound basically says that for any policy evaluator, no matter what we do from the batch data, okay? So inf over v hat, for no matter what evaluator we use, then sup over the model, there always exists a hard instance, okay? No matter what we do, there exists a hard instance such that the policy evaluation error is at least this large, okay, with high probability. And so basically, by comparing the upper and lower bound, we see that they basically match in the worst or in the hardest instance. Okay, and we also show that this lower bound also matches with the known Craméral lower bound in the tabular case. Okay, so now comparing the upper and lower bounds, now we basically could conclude that we know sharply what's the statistical error for off-policy evaluation using a linear function class. Okay.
So there was a question in the chat, and I do have my own question. So on the previous slide, I noticed maybe that's also the typo that it says that mu bar is the occupancy measure. Mu pi is the weighted discounted state occupancy measure. So that
that's a typo. Yeah. So we had a version of this result for both finite horizon case and the discounted case.
Yeah.
So in the discounted case, all the measures are weighted discounted measures.
Okay.
Yeah. Thank you for catching that.
Yeah. So the other question was for the next slide. The question was, what is this class N of M that you take the supremum over, and what is this M prime?
Okay. Yeah. Good question. So the full theorem is pretty lengthy. So we basically had a localized lower bound. So we actually say that if you give me any instance M, then we can find another hard instance in its neighborhood. And we could characterize how big the neighborhood is. It's actually a very small neighborhood. So for any instance M, we find another instance M prime close to it. And we show that those two instances are actually pretty hard to tell apart, although they have different values of the target policy. So this is a localized lower bound analysis.
So could it be that you would have a stronger result if you didn't restrict the neighborhood here? Like the lower bound, the CH squared maybe could be inflated or something? No, it can't be, because the upper bound already bounded from above, or I don't know, like...
Yeah, I think it's a matter of presentation. So we could present it in a way that's more instance dependent. But we also wanted to match the minimax upper bounds within this whole class. So that's why we present in this form. But this basically says that this kind of hardness not only applies to like one particular extreme instance in the whole family, but nearly for most instances in family, there's another hard one close to it. So I think this is like a hybrid between an instance-dependent lower bound and a worst-case minimax lower bound.
Yeah, so I'm also trying to parse this statement. So an instance is an MDP and a behavior policy and the target policy. So like all of these combined. And I guess once you combine all of these, then this chi-squared distance is a fixed number, right? So it is not.
Okay, so to parse that, we probably need to look at the full statement of the theorem.
Right.
So in that one, we actually fix an arbitrary target policy, but we could construct an instance with a particular generating policy. That makes things hard.
I see. So this says that that if I give you like an MDP with some chi-squared distance between like mu pi and mu bar, then you're gonna give me a hard example on which this holds, or this is strong.
Yes, we can do that.
Right. Okay.
All
right. Yeah, I'm gonna look at this. Yeah, if you don't want to spend.
Yeah, it's a pretty lengthy statement.
Right. Okay.
Yeah, very good question.
All right.
Yes. So this is how the proof works. So basically, we start with any given MDP instance with known model little p, and we try to perturb it into another similar instance p tilde. Okay. So then we try to optimize this perturbation to make the problem hard. So to do that, first we try to do a likely ratio test to make sure that the two instances generate similar data. And with that as a constraint, we also look at the gap between the two values, which is another function of the perturbation. So we try to maximize the gap subject to the constraint that the perturbation still makes the perturbation small so that the two instances are similar. And then we figure out, okay, there is another particular way to perturb the instance to make the problem hard. And then we get the lower bound. Okay. So that's the story for linear regression for batch RL. So
can I ask one more question? So the upper bound that you presented, it should work even if you don't have any fixed policy generating the data.
Yes, right. We only need this mu bar. Yes, we only need mu bar to be an invariant measure. The underlying we could have more than one underlying policies, but as long as their opposite measure converges to mu bar at a reasonable rate, this should work.
Or maybe just like you take the average over the different n trajectories, and then you define mu bar that way.
Yes.
And then that's sufficient, I would think.
Yeah, that would be sufficient. But we do need those episodes to be independent.
Yeah.
Right.
Yeah.
Although the episodes could be generated by heterogeneous policy, we only need their average opposite measure to converge to mu bar.
Yeah. Okay.
Okay. Okay, so finally, before conclusion, I just want to mention a couple of our other works in which basically the message is regression is sufficient to make RL work. So we talk about linear regression with fitted Q iteration for off-policy evaluation, but regression actually works for general online RL. And I'm sure in online RL, we deal with a more complicated problem. We care about the regret of a learning algorithm. And the algorithm has to be collecting data while learning. And we have more challenges because we no longer have independent episodes. And also we don't have automatic exploration. So we have to care about exploration. So in batch data, we don't care about exploration because we cannot explore, we only have batch data. So somehow the limitation in batch data somehow makes the problem simpler, but online RL is definitely harder. Okay, but regression still works for online RL. So one result we had is we show that if we work with linear MDP, and then if we try to embed the unknown transition model into a finite dimensional matrix, okay, so that's the linear MDP model. And then we can simply estimate the model by regression and explore. And the algorithm is, we call it matrix RL. It's a model-based algorithm for linear MDP as opposed to model-free algorithms. So again, it works pretty much like Q-learning type of methods, because every time we try to update Q functions, we're updating Q function using an estimated model, which is this M hat, an embedding matrix of the true transition model onto a linear space. And then we just add optimism. And optimism is, and if we think about this optimism bonus, actually the optimism bonus can be viewed as a relaxed version of that chi-square divergence from batch RL. Okay, so if we do this linear model regression together with a little bit of optimism, one can show that we can reduce the regret of exploration in RL to poly-D dependence after model regression onto the finite dimensional linear space. Yeah, and this is something we expect. Okay. And more recently, in a joint works with actually with Chaba, Alex, and I don't know if my other co-authors are in the group. So we show that actually regression also works for RL with very general nonlinear models. Okay. So in general, if we think about model-based RL, we could have a general class of transition models. We can call it this capitalized P. And to make it a bit more concrete, we can think about, we have a parameter theta that is parameterizing the transition model. Let's say that theta are really just weights of a neural network. But in general, this capital P could be a non-parametric family of transition models. And the general framework of model-based RL is going to be that we iteratively estimate models from latest data set. And then we use our estimated model for optimistic planning. Okay, so this is the general framework for upper confidence model-based RL. Okay, so we try to ask a question. So can we make this method work using regression? So we already know that in the case with linear MDP, we can embed everything into a linear matrix model, and then we do linear matrix regression. But can we use nonlinear regression to feed the model? And the short answer is still yes. Wait, okay. And this is the algorithm. So I will just mention it like using 1 minute. Hopefully, maybe someone could talk more about it in a full-length talk, because there's a lot of interesting insights from this result. But basically, the story is we can do nonlinear regression for estimating the model of the unknown RL problem. And another interesting point is, okay, so for example, theta is the model estimator. That's estimated by regression. And we're going to estimate this model estimated theta by doing nonlinear regression with the target y defined as the estimated value function of the next state. So this actually helps us a lot, because we have a nonlinear model, and usually it's hard to do regression for nonlinear model. It's hard to choose the target. Usually we can do MLE, or we can try some other means. But if we happen to use our inexact estimated value function as the regression target, and then we just do regression, which could be a highly nonlinear regression problem. Okay, then we estimate the model, and then we build confidence set, and then we do optimistic planning as usual. So it turns out that this approach actually works with regression using changing targets, using estimated value as targets. Okay, so this is our recent SML paper, and I like to take this opportunity to promote it. Okay, so this is a pretty abstract algorithm, but incidentally, so this algorithm is actually a theoretical abstraction of mu0, which is the state-of-art deep RL algorithm for solving a collection of Atari games and also games like chess, Go, and shogi. So basically, mu0 is a model-based algorithm which doesn't know the model of the game to begin with, but learns the rule by playing. And also, it actually implements a variant of value-targeted regression to learn to fit the rules of the game. So our theoretical method could be viewed as really just a theoretical abstraction of what's happening with mu0. Okay, so we actually could prove that value-targeted regression works efficiently for model-based RL with a general family of models. So the regret depends on a notion of alluder dimension of the transition, the family of transition models. And also it depends on the log covering number of the family of models. So the notion of alluder dimension was proposed by Russo and Van Roy in Bayesian optimization and Bayesian RL in 2013. And it turns out to be a very nice characterization of the complexity of a general nonlinear model class. And there are a lot of technical details I'm omitting, so I would like to invite you to read the paper. And so I think the short answer is we actually know that regression using value as target actually works for online RL, even if the model is not linear. Okay. So finally, I think a very interesting message I hope to convince you is that regression works for RL. So in the clean, simple problem, which is batch data policy evaluation, doing regression with FTQ iteration is going to give us Minimax-Optimal Estimator. And that estimator is actually equivalent to a number of important sampling-based algorithms. Okay, and we could measure the hardness of problem using a mismatch in the feature space. And turns out that that mismatch also shows up in the lower bound. So that's the central quantity determine the fundamental complexity of the problem. And further, regression actually works for the harder online exploration problem. So with linear model, we get d square root of t result by doing linear matrix regression. So with nonlinear models, so things are more complicated, but we can still make regression works with value-targeted regression. Okay, so that's the end of my talk. Thank you very much.
All right, thanks very much. And give Mengdi a little bit of a pause.
Thank you.
Yep. Yes, thank you. That's great. So I was wondering if you could give us like some idea about the proof of this upper bound, like what is the key, and how does this chi-square divergence pop up exactly?
Mm-hmm. And then this one.
Yeah, like the upper bound.
Okay, this one.
Uh-huh.
So I think this proof is pretty brute force. Okay, so basically we're just analyzing the efficiency of a plugin estimator, right? So we have a p hat, right? So our estimator is a function of p hat, right? So we really only cares about the concentration of this function of p hat to the true value. Does that make sense? So then naturally one should, so a natural way to do this is one can use leave one out analysis, or one can try to do a Taylor expansion of that function. And then one can analyze the leading error term, the non-leading error terms. So this is, I think that this analysis is really trying to decompose the error by analyzing function of data minus function of population distribution.
Right, and I guess at some point, what you gotta really analyze is like the distance between this mu bar and mu pi in terms of like so how these are constructed under the estimated model and the true model.
Yeah, that distance shows up. I think this dominating term in the error is really a shifted error from linear regression. So that chi-square actually shows up from doing linear regression from one data, but using it for prediction from another design distribution. So that's where the dominant term shows up. And this dominant term turns out to be not much different from really linear regression with domain adaptation.
Right, and does it show up in this dual form, in this variational form, or its primal form? Well, I guess I'm sort of like curious what the primal form or the dual form this chi-square distance is.
Okay, so our definition, the soup over F in Q is a dual form. So in the primal form, it will be the projection of the density ratio onto the Q space with a particular Euclidean norm with the norm L2 mu bar.
Right. Okay, I think I understand this one a little better.
Yeah, so that projection, that primal form is easier to understood, but I actually think this dual form is more generalizable to potentially nonlinear function class.
Right. Very nice. Okay, so let's see if there were some questions in the chat. I don't know, Chaba, you were following?
I do have my own question. I was following a little bit the questions in the chat too. So I do have one question. Like you mentioned at the beginning, realizability or unrealizability, that you can extend these results to the unrealizable case. I'm particularly interested in the result that's shown now. What happens if you're in the unrealizable case?
In the unrealizable case, there will be an additional Bellman error. And that additional Bellman error is, again, evaluated using a particular norm that is determined by the population distribution of the data.
Okay. And so so we have this curve of horizon that says that fix an MDP, fix two policies, let the horizon grow to infinity. And then somehow they diverge, like in general, there will be a divergence with the horizon, and like it becomes a harder estimation problem. So what happens here with this unrealizable case? Because I think that what's nice about the realizable case is that somehow the horizon suddenly doesn't matter. You just measure this high-squared divergence, and the high-squared divergence is not a function of age, right? Like it's
actually, that chi-square divergence could grow exponentially in age if we're unlucky.
Even for the realizable case?
Even for the realizable case, yes.
I guess
think about
the tabular case is a special case, and in that case, it can go unboundedly, right? So that hides a dependence on age.
Yes. Like, for example, if we're doing tree search, right, then the true policies could become like infinitely mismatched as age grows. And that will show up in that chi-square term as well.
And so the other worry that one might have is that you have this unrealizable case. Maybe you have an epsilon error, and epsilon, 1 over epsilon to the power of h somehow shows up or something like that. Would anything like that happen? Or you have finite characterization, and the worst case is 1 over epsilon to the power of h. You're like, do we understand how this works?
I think if the model is unrealizable, and if we have misspecification error, and definitely this error could be exponential if we are unlucky. But one can evaluate that error by, so basically the final approximation error due to model misspecification depends not only on horizon, on the misspecification error itself, but also on the distributional mismatch. For example, if we can evaluate that our data are well conditioned, then the approximation error will be smaller.
Yeah, I mean, like, it could be that you're so lucky that the behavior and target policies are the same.
In that case, that mismatch will be 1, I think.
Right. I mean, like, this high square is just 0, and even in the analyzable case, you should be fine, I guess.
Right.
Because you can just have a Monte Carlo estimator anyway, so it's like if the regression estimator would be worse than that, that would be a bit of a letdown. But
yes,
yeah,
exactly. So basically, I think that mismatch is controlling both the statistical error and the misspecification error.
Yeah.
And that term shows up everywhere. So it actually, so in the big O, for example, this estimator is actually biased, but the bias is on the order of 1/n, so it's very small. And if that mismatch, if mu bar is well conditioned, then one can actually show that the bias is tiny compared to the statistical error.
Yeah. Okay, Heng Shuai is asking last minute question. Does LSTD enjoy the same bond?
Which LSTD?
I mean, yeah. Heng Shuai, do you want to explain your question?
My question is for basically under the same assumption that P pi F also in the space of Q, where this theorem was derived, will LSTD, under the same kind of assumption also will achieve this error bond, because LSTD can also be applied to this OPE problem, right?
Depends on which norm you use in LSTD. So I think in general, they are not equivalent, but probably with a particular norm or a particular empirical loss, they could be the same. I didn't analyze LSTD.
I would think that like the finite horizon setting is very special in this case. LSTD and this fitted Q iteration are kind of the same. I don't know, Heng Shuai, you said that they are different, or?
I think my intuitive guess is they are similar, should be similar.
Okay.
Yeah.
I guess we are on the same page. We think that it's kind of the same. Yeah. Maybe exactly the same.
Okay.
No, but when we do LSTD, we could use different norms in the least square. So I think for particular choice of norms or empirical norms, they should be similar or the same, but they are not the same in general.
Okay.
So Ahmed had a similar question. I don't know if that LSTQ was a typo or is that an actual algorithm? Ahmed, can you speak up and clarify?
Yes, yeah. Actually, LSTQ is the same as LSTD, but just to estimate the Q value instead of the value function. So it's this. Yeah, it was actually the same question. What's the difference between the version of FQI in this paper and LSTD? And I think in the finite horizon they are the same, because I think LSTD is using the closed form solution of the L2 regression. So it's least square regression, and I think it's yeah, I think they are the same actually in the finite horizon. And there is already like sample complexity bound for LSTD, but not in the off-policy case, at least in the on-policy case of like the work of Alessandro Lazaric. But yeah, so just my question was, yeah, if there is any how could you like relate this sample bound to the sample complexity of LSTD maybe? Yeah, but maybe it's I don't know.
Oh, I just didn't analyze LSTD. So we had one upper bound matching one lower bound, then we are happy. Yeah, probably one could extend this to LSTD as well.
Okay. Okay, thanks.
So Yaqi Duan, Iran, you had a question.
Yeah. Yeah, so I was just like wondering if the lower bound proof technique has anything to do with smoothed analysis. So in TCS, in smoothed analysis, once when you are given a problem instance from adversary, you can assume that the natural perturb, and as long as you can solve that perturbed version of the problem efficiently, you think that okay, you can solve it like efficiently. So like since in the lower bound proof, you assume that like you construct a similar instance by adding this phi times xqs and then optimizing the perturbed direction. So I was just curious if there's any connection.
So I'm not very familiar with the smooth analysis, but the idea of constructing similar hard instance is a pretty common approach for establishing lower bounds. I mean, for establishing like generalization error lower bounds, zero error lower bounds, and even computational lower bound. So I think in that sense, that proof technique is basically pretty general. But maybe there are something specifically related to the smooth analysis, and I'd love to learn about it.
Okay, thank you.
Thank you.
By the way, is this a high probability bound that we're looking at in this theorem? Is that per bound?
It's a high probability bound, yes.
Okay.
Yeah, there's a log 1/delta, which I didn't show.
Yeah, it multiplies the root 10 thing.
Yes.
1/10 thing.
Actually, yeah. Sorry, I may have another question. So I think that so in the control case, for example, we need also like extra assumption about the state. Like we assume that we have anchor state, but here in the off-policy like evaluation, it doesn't seem that we need this this assumption. So do you comment what's the difference between the two? Why we don't need this assumption, but in the control case, well, it seems that we add also the anchor state assumption.
Okay, so what's the definition of your anchor states? I mean, anchor states have a number of different definitions to my best knowledge. So I think probably we mean that we are doing generalization of a function over a linear space, right? So then what we need is, for example, either we have anchor states, so we can extrapolate from anchor states, or if our data already has good covariance matrix, that means that any fitted model we obtain by fitting the well-conditioned data is already a good estimate of the true model from any dimension or most initial state and action, then we're good. So does it make sense? So basically, okay. This well-conditionedness in the data is what we need. And this well-conditionedness is implicitly assumed in the mismatch. Let me come here. Okay, so in the finite dimensional linear model, this mismatch is bounded by a relative condition number. So this requires that the target policy and the data are close in their covariance space, which basically says that the problem has to be well-conditioned. So whenever we have well-conditioned problem, we have good generalization properties because data gives us enough information to do the prediction.
I guess maybe more generally, the question is like, how come that there is such a big difference between policy optimization and policy evaluation? Is that correct, Ahmed? Is that what you're after?
Yes, I think because I remember there is one of Mengdi Wang papers like about control with generative model. I think. I think it's model 3, and they use actually the assumption of the anchor state to interpolate between different states. But in the case of the of just policy evaluation, like I was a bit surprised that we don't need this assumption. But I think the answer is
wait a minute. Do you mean the anchor state assumption we made in the paper to get sample optimal Q iteration? Is that the one you have?
Yes,
okay.
This one, yes.
So even without that assumption, we could get pretty good sample complexity, but misses the lower bound by one factor of h. So that anchor condition is needed only to close the final, to reduce the final, to close the final gap of h. But that anchor condition wasn't needed to get okay sample complexity. Does that make sense?
Okay,
so
I see.
Yeah, and also the two problems are indeed different, because so in somehow, like when we do like policy optimization, the minimax sample complexity is more worst case, in the sense that we have to care about all possible target policies, and one of them could be optimal, right? So if the target policy just happens to be bad or concentrated on one state, to make sure that we still get good results, we need to make sure that our data has to be representative of all possible target policies in the worst case. So in that case, we have dimension D showing up in the sample complexity directly. But in off-policy evaluation, we only have two policies, and it's really this particular fine-grained mismatch between the two policies are showing up. We're not making sure that our analysis holds for all possible optimal policies. So somehow this batch evaluation problem is a little bit more instance dependent. Yeah, I hope it makes sense. We can talk about this offline.
Yeah,
there's some subtlety there.
Yeah, okay. Yeah, that makes sense. Thank you for the answer.
Thank you.
Yeah, so I have a question regarding this on-policy and off-policy differences. So your upper bound depends on h squared in this
yes,
but also the lower bound. But for the on-policy thing, that should be just h, right? So you just take an average, and by having things inequality, you just get
no, not really. For on-policy, it should be h to the power of 1.5.
Oh, okay.
And also in the generative model case, that should be also h to the power of 1.5.
But that's not. Is that like the value estimation or estimating the value function under some norm?
Okay.
Because here you're just looking at the value in the initial state, right?
Yeah. So if we want to estimate, if we want to do policy optimization, or if we want to figure out the worst case target policy, they are actually different. Okay. So there is indeed some subtlety right here. So so actually we had some discussion, and we feel like there seemed to be a subtle difference between on-policy and off-policy. So for example, this h square, so we actually had a lower bound showing that where this h square is sharp, little c is constant, and chi-square is constant. But in that lower bound, we construct behavior policies and target policies that are drastically different. In that case, we have h square, which was actually unexpected, because we knew from generative model settings, the right dependence should be h to the power of 1.5.
Right.
Okay. But another subtlety is this chi-square somehow hides dependence on h. Because, for example, what happens at the first stage 0 will have a higher impact on the overall error than what happens at a later stage. So this chi-square could be exponential in h. It could be poly in h. But we cannot say that it has absolute no dependence with h.
Right. Yeah.
Okay. So I would say this h square is actually sharp, but there are instances where two policies are similar, and then this bound could reduce to h to the power of 1.5.
Right. Gotcha.